Hello and welcome back to Data Science with R for Social Scientists. In this session, we want to focus on exploratory data science. And when you go back to one of the first slides that we looked at, you can see that we have this gray rectangle around the process of data science, which is labeled understand. And this is really the goal for exploratory data science. You want to look at raw data, and through transforming, visualizing, modeling, you want to gather an understanding of the data. Now, this is perhaps easier said than done, and the book gives a few hints what this process might look like. So, exploratory data analysis involves 3 steps that are in this iterative circle. You first want to generate questions about your data. Then you want to search for answers by visualizing, transforming, and modeling your data. And then you want to refine your questions or find entirely new ones based on what you've already learned. Now, when you think back about the plot by John Byrne Murdoch, at the time this was published, the data was already widely available. Yet there were worldwide very few experts who actually understood what was going on, and they found it hard to communicate it to governments and to citizens. John Byrne Murdoch was able to, using ggplot, to visualize the trends and really show that the catastrophic outcome that Italy saw was just a couple of days ahead for countries like Germany, the US, and the UK if they didn't do anything. He also showed that some countries broke the general cycle, like Japan, Singapore, and Hong Kong, because they implemented measures to counteract new infections with COVID-19. So what other strategies can we use to get going with exploratory data analysis? It tells us that we should look what type of variation occurs within our variables. And then it tells us to ask what type of covariation occurs between variables. So in essence, we want to see the patterns in each of the variables, and then we want to see if some of the variables interact with each other. I would add a third point to this. I think we should also think what plots and tables can we use to get to these variations. This is of course also done in the book, but I just wanted to highlight that rather than starting with the raw data, you could also start with your toolbox, with the things that you've already learned in this course, and then just iterate over them and then see what is applicable to your specific data set. The first hint to get a better idea of what plot can be used to get a better understanding of the data is how the variable looks like. Do we have a categorical variable or do we have a continuous variable? For a categorical variable, we can see the variations, so basically how the variable changes over the data set by counting how often each of the categories is used. For this, the bar graph is a very solid option. For a continuous variable, it looks a little bit different. We can also use counts, but in this case, it is not a bar graph, it is a histogram, because what we are doing is to transform basically our continuous variable into a categorical one by dividing the data set into bins. In this case, we divide it into bins of 0.5. So we have a bin from 0 to 0.5, then one from 0.5 to 1, and we count the instances in the data which fall inside of this range. For covariation, we have a lot more options. Again, we can check out which kind of variables we want to compare. And the first option here is that we want to compare a categorical variable with a continuous variable. In this case, the frequency book is a good option, but as the book explains, it sometimes makes more sense to look at density. For example, if the counts are very different and the line would be squished at the bottom, so you wouldn't be able to see the variation of the continuous variable over the different categories. A really robust option is the box plot, which is especially liked by statisticians And if you stay in academia, you will probably see a lot more of the box plot. However, outside of academia, it is not widely used because you really need to explain in very detail what the different elements of the plot needs, what the different elements of the plot mean. So if you want to go outside of academia, then a violin plot, for example, or a rich plot might be a better option. Then next we have categorical variables versus categorical variables. In this case, we have the cut of a diamond versus its color, and we can use a special geom called geom count to visualize how often each of the categories are used together. Maybe a better option is to use a so-called heat map, which we can do with geom_tile, and we will look at this later on. Finally, if we want to see covariation between two continuous variables, we have again a couple of different options. First of all, we have the scatter plot, which is really useful for smaller data sets, but it quickly becomes difficult to see the individual points because of overplotting. This is solved by two other plots, which can be called by geom_bin2d and geom_hex, and they both basically work like a histogram. They cut up the visual space into smaller units and then change the color of these segments of the plot according to how many cases are in a specific X and Y spot. And then finally, we can use the box plot again for continuous versus continuous variables. So here again, the idea is that the continuous variables will be cut up into categorical ones, and then we can visualize the categorical variables using a box plot. Again, you can also use the violin plot, or you can try to add another geom, like a geom quasi-quadrant, which is from the GGB swarm package, and it basically overlays the box plot with the individual points, but tries to evade overplotting. You can think of it as similar to the jitter plot that we learned about in one of the last lessons. So let's start with exploratory data analysis. We can use a new data set for this because we don't just want to repeat the old plots that we've already learned before. We want to create new ones to really learn what's going on inside a data set. And for this, I turn to the animal kingdom. We're using the Palmer Station penguins. This data was collected by Dr. Kirsten Gorman at the Palmer Station in Antarctica. She observed different penguins while at the Palmer Station and made this data set available, and it has turned out that it is really great to learn of the different plotting strategies in the tidyverse. So in this data set, we have three different kinds of penguins. We have the chinstrap, the gentoo, and the adelie. And we will look at the beaks of the penguins, which is measured using bill length and bill depth. So here we are back in R, and to begin, I create a new Markdown document. I call this Notes on Exploratory Data Analysis. And I begin by deleting everything from the example here. Something that was bothering me in the videos before is this little line here, and I just learned that you can simply disable it by going into global settings, then code, display, and show margin. There we go. And now that we got rid of this line, we start by loading the data. And this time around, I also want to use a couple more headlines to structure our notebook here. So let's get started with data. There are essentially two ways to get to this data. Either we can again install the package which houses this data set and which is called Palmer Penguins, and I'm installing it here. Or we can go to the GitHub site of the Palmer Penguins package. GitHub is basically a website that houses a lot of different code, open source code in particular. And here, most of the R packages that you can install through CRAN are also available.
Here we have the Palmer Penguins package. You can see that they recommend to install it, as we just did, but you can also go into one of these folders here. This is basically the structure of the whole package, and you can go to inst and xdata. And confusingly, you can't really right-click and download any files from GitHub, and this is why I'm showing you this. So next time you find a dataset on GitHub, remember, you can't right-click and download it here. When you do so, you will basically end up with an HTML file which shows you the rendered form of the dataset and not the dataset itself. What you need to do instead is click on this once and then click on the raw button to get to the data. And we can copy this link here, the link to the dataset, and we load the data by using one of the commands we learned last time, which is rio import. And when we import this now, let's call the dataset penguins. You can see that we have our new dataset here. Clicking on the View tab, you can see that we have 344 entries and 17 columns in total. So we have a description of the species here. We have the region where the species was found. We have the island where a particular penguin was found. We have a stage. We can look later what this means. Clutch completion, date of the egg, and then we have a description of the physical features of the penguin. So we have culmen length, culmen depth, flipper length, body mass, sex of the penguin, and then a comment column. So how can we get to analyze this dataset? How can we do exploratory data analysis on this? First, let's save this file. We're technically in the 7th session now, but let's stay in our numbering scheme and call this 6EDA. So once again, how can we do exploratory data analysis on this? How can we understand what's actually in the data? And to get started, let's open our toolbox. What I have here are the 2 slides from the lecture, which list all of the different plots that we've learned so far and sorts them into categories to show you how you can use them to visualize variation and covariation for different kinds of variables. What I want to do here is basically start from a tools perspective and think, okay, what tools have we learned so far and how can we use them on this new data set? So what I want to do is I will copy all of the different plots into our document and use the different categories as headlines in our Markdown file. And here we are back in RStudio looking at our Markdown file. I can also show you a useful little tool which is built into RStudio, which is to show the document outline. And here you have now the different headlines in the hierarchy that I've chosen. So you have a first order headline, second order headline, and third order headlines. When I now switch to variation, you can see that this is highlighted, and I think it is useful for the rest of the video to keep this open so you will always know where we are currently looking at. As you can see here, I started my data exploration section with the variation part. We will look at categorical variables, continuous variables, and then move on to covariation and look at categorical versus continuous variables with the different plots that we have for this job. Then we will look at categorical versus categorical variables, and finally at continuous versus continuous variables. Now, RStudio already displays us that there is a package missing. What I probably haven't mentioned so far is that ggplot, which is itself an extension to R, has its own little extensions. Those packages provide additional geoms or additional themes and basically build on the same logic of a grammar of graphics, but just add extra features. And incidentally, some of these features will eventually end up in ggplot itself, but ggridges hasn't made it that far yet, so let's install it to get rid of the message. While this is still installing, we can already have a look at the dataset. And here, let's take a step back and quickly discuss how we can differentiate between categorical and continuous variables. The first good indicator if a variable is categorical or continuous is the data type it has been saved in R. So what we can do is we can open the little overview here in our environment window and make it a little bit larger. And here at the beginning, you can see that this is a character vector, this is an integer, and further down we have numerical vectors. But we can also see it right here. We can see that the species, for example, is a categorical variable because it is made up of a character vector. So there is no natural continuous scale where you can differentiate between one species of a penguin and another. Instead, those are categories. And then when you look at column length, for example, you can see that this is probably a continuous variable. It could also be indicating different categories which are saved as a numeric value, but usually when you look at a numeric vector, these are continuous variables. You can also see that probably not all of the variables are interesting. For example, we have the study name here and a sample number. These basically indicate to whomever collected this data where a certain data entry came from, and there's probably not much that we can do with it. We also probably don't want to analyze the comments section unless we can find a very obvious pattern in here. This basically leaves us with the species, region, stage, clutch completion, date egg, culmen length, culmen depth, flipper length, body mass, sex, and then possibly we also want to include those two variables back here. How can we decide if we want to include those two that don't really have an obvious name? Well, usually it's a good idea to look up what the columns mean on the website where you got your data set from. In this case, we can also look at the help file from the package by typing in Palmer penguins, 2 colons, and then penguins raw, and then we set a question mark at the beginning to open the help file. When we look at this help page now, you can see that once we scroll down a bit, you have an explanation for every one of the 17 variables contained in this data set. When we go further down now, we can see that a number denoting the measure of the ratio of stable isotopes 15N and 15,4 is what the column delta 15N means, and delta 13C is basically equally cryptic. So usually I would encourage you to find out more about these two variables, but since this is mainly done as a practice here, I think it is okay to ignore those two variables for now and not get any further information on what the description means. What I was also immediately interested in is the date egg, and here I can see a date denoting the date study nest observed with 1 egg sampled. And I was hoping that this would indicate when a penguin is born or when the egg was laid, but it seems that the variable is not that useful for us because it basically just indicates when the observation was made. So then what I can do to select the variables that are interesting to me is I can first of all find out the names of these different columns in here by using the colnames function and then the name of our data frame. And then what I want to do is to copy the column names of the variables that we are interested in into the two categories, categorical variable and continuous variables, so that we know what we have here. So now that this is done, we can start plotting. First I need to remove a bit of leftover code here, and then we can put the data set in here, which is called penguins now. And we can make our first bar plot by mapping the species to the x-axis here. And here we now get an error that ggplot could not find the function ggplot. And what this should tell you is that I forgot to set up this R Markdown file correctly, because what we need to do, of course, is to load the tidyverse package first. And now that this is done, we should be able to look at a nice plot. What you can see here is that we have more Adeline penguins than Gentoo, and more Gentoo penguins than chinstrap penguins. And now that we have this first plot done, we can basically copy the plot and do one of these for each of the variables that we are interested in. And here we go. After looking at this plot, we don't immediately see interesting patterns, but what we can see instead is that the region variable as well as the stage area, as well as the stage variable, is probably not useful. And going further, we don't have to look at this again, because the variation here is that there's no variation. We only have one kind of observation here. We only have one category to look at. So it is impossible to draw any conclusions from this, and we can safely ignore the variable from now on, because all of our data observations have this category. So I can write a note down here to tell me that I can safely remove the region and stage variables, because they have no variation at all, and so nothing that we can work with. And this is generally a good practice. You should write an R Markdown document like you would write a different text, where under each plot you write a description of what people can see and what the plot means. And then at the end of a section, you write a small conclusion explaining in more detail what we've learned in a specific section. Before we move on to the next section though, I want to have another look at the variables that we selected. We have species, region, island, stage, and sex here. However, what I forgot is the clutch completion. So let's have a look at the clutch completion and also find out why I haven't looked at it so far. Let's make a new plot by copying the last one here and putting this at the end. And then the question is, how do I write clutch completion here? Because when I do this, it will tell me error unexpected symbol in geom bar, and the unexpected symbol here is the white space. This is generally a problem with datasets that come in raw or kind of uncleaned, because often people think it's a good idea to have column names with white spaces. But this makes it a lot harder to work with them in R, because here the white space indicates that you're done with one expression and want to start the next one. So there are basically two alternatives on how we can fix this. The first is we can use penguins, and then we can use the $, which is used in R, to select one of the columns. And when we do this now, the autocompletion wraps our column into those characters, which look a little bit like quotation marks, but they're actually not. And when we use this now, R will recognize that clutch completion is the name of a column in our data frame. The second solution to this problem And the one I usually prefer is to do a bit of data cleaning before we move on to exploration. So what I want to do is to create a new object called penguins clean. Then we take the old data frame that we already have and we use the rename function from dplyr to rename the column names that have white spaces into something that makes more sense to us. So what we can do here is we say we want clutch completion, we want to rename clutch completion to clutch. We rename Kalman length in millimeter to bill length as indicated in the slides. Kalman depth is likewise renamed to bill depth, and so on. And when we look at this data frame now, we can see that the variables we are interested in have better names, which makes it easier to plot them. However, now we have this completely useless object here, which is the penguins data frame, and we will probably never again work with this. So we could save one step and one code chunk by simply copying this over and cleaning the data frame on the fly. When we do this now, we can go back to the last plot that we made and replace the cumbersome column name with the new one we created. Now, in most projects, cleaning the data is actually not that easy, but can take considerably longer. This dataset was relatively okay though, so with a couple of lines of R code, we managed to get nice column names that we can work with from here on. And as we've also seen, working with R is not always a linear process. We only noticed that the column names were problematic once we got to plotting, and then we went back and fixed it while loading the dataset. So now let's have a closer look at the plots that we created. What we can see here in the first plot, what I don't like is that the penguin names are quite long. So we have their normal names in here and then the Latin names and brackets behind them. So we can think about fixing that later. Region, of course, we want to remove. The island looks fine to me. Stage, again, we want to remove this. And then when we look at sex, we can see that for a couple of penguins, the entry is missing. We have an NA here. And for the clutch, we can see that there are many more completed ones than non-completed ones. So then let's move on to continuous variables. And here we can do the same thing. We can systematically go through the continuous variables and see the variation of each of them. We can start with the first one here, or rather the second one, because the first one is clutch completion, which we just determined is a categorical variable. So we want to go with Kalman length now, and I can just first remove this code. We can just plug in the dataset here, and then we can put in bill length, which is the new name of this variable. So here we see this is pretty roughly a normal distribution. So we have a few outliers near the 0 point and then the very large one. Actually, this is not 0. This is, so the minimum scale is around 30. So a few penguins that have a rather short bill length, and then a few ones that have a really long bill length. and then a lot in the middle. We also see the ggplot complaints here. Remove 2 rows containing non-finite values. This is a little bit confusing. When we look at the actual column here, we can see that there are NA values in this column. And in this case, non-finite values basically means it removed NA values here. So then again, we can copy this code and go through the rest of the variables. We next look at build depth. This looks pretty much the same. We could also think about decreasing the bin width here, because it seems that we have relatively few bins, which means that we can get a more detailed picture by decreasing the bin width. And remember that bin width is always measured on the same scale as the x-axis. So when we decrease this now, we get smaller bars and we get a clearer picture. We can see the spike here in the middle that we didn't see before, and also this valley where relatively few penguins have this bill length. Again, we see the complaint here about non-finite values, and we can also change this now. Let's use the pipe for this and some dplyr code. We filter and we want to keep only the rows where our variable is not NA. And when we look at this now, the plot looks exactly the same, but the warning went away. I'm copying this over to the first one. And of course, here we have to switch out build depth with build length. Oh, yes, of course. Then we want to have a look at flipper length and body mass. Again, it seems we have some NA values here. And here we can see that for body mass, our bin width is obviously too small. So when we check the column again and we look at body mass, we can see that the variation here seems to be between 2700 and 6300. So probably a good bin width to go with is 100 here. And there we go. This looks much better. We have fewer columns in total, and the patterns become more obvious because each one is a bit higher. And here again we have a few NA values. What I'm wondering now at this point is if there's a connection between the NA values in those different columns. And you can basically not sort here in the viewer for NA values. So no matter if you have the large ones on top or the small ones on top, the NA values won't show up here. But what you can do is you can scroll to the end, because whenever you sort the view here, the NA values will be located at the bottom here. And as we can see, there are basically 2 penguins here for which there were no measures. And we can see that both have the same comment here. So that means that we simply don't have data for these 2 penguins, and we can probably just remove them from our sample. So once again, we go back to the beginning of the document and we add another line removing those two penguins. So what we want to do here is we want to remove the penguins where the bill length and the bill depth and the flipper length are all NA. Actually, body mass is in here as well, so let's play it safe and remove only the penguins where all of these are missing. I can see here now we have 344 rows in this data, and now we have 342. So those two were removed. And when we go back to our plots, we already fixed those individually. But when I scroll further down, the flipper length, for example, when I run this now, we get no complaint because there are no missing values left. And here as well, it looks like it's a good idea to fix the bin width. And I'm guessing that 10 probably looks good. No, that's too much. Let's go with 1. 1 looks relatively fine. I think with 2 we should be golden. Yeah, that's perfect. So here once again. And what you can see now is that the variation of the different variables obviously differs by a lot. So body mass is just measured in a completely different unit than flipper length, for example. And what we can also see is that we have something that looks like clusters. So we have one distribution here and we have another distribution here. And the idea this gives me is that maybe these clusters have something to do with one of the other variables. One obvious choice would be the species. Note that we have 3 different species here, so it's a little strange that we only have 2 clusters. And this seems to be relatively consistent over the different other variables. Here, maybe we have 3 clusters, but we don't know yet. But this is what we can do in the next section here with covariation. And here, once again, we can go through the different categorical and continuous variables. So what are these? To remind ourselves, I prepared something in advance, which are the categorical variables without the ones that we decided to remove, and the continuous variables together with the new column names that we chose. So we can plug this into our script here. Let's choose the penguins data set, and then we want to go with bill length. And as I said, I suspect that the species is quite important. So the second column that we map to aesthetic, in this case the color aesthetic, is the species. And let's run this as it is. Now, this doesn't make a lot of sense. And again, the bin width is at fault here. We can go back to check for the bill length. We choose a bin width of 0.5. which in the histogram looked pretty good. So let's do this here as well. And when we run this now, we get a much nicer plot, and we see immediately that my suspicion was probably right, and that we have not one distribution of bill length, but we actually have 3 different ones according to the species. And we can see that for Chinstrap and Gentoo, the distribution looks relatively similar in this plot. So this is why we only saw 2 distributions, because Adderley and the other 2 are markedly different, but Chinstrap and Gentoo are relatively similar. So which plot should you choose to visualize this? I think this one is already looking pretty good, but let's go with the next one, and let's copy the first line over. So we can actually copy this bill length, then we leave the y value density, because what we're doing now is a density plot, but we choose species for giving the color and 0.5 for the bin width as before. This looks relatively similar, but remember that before we had the count here and now we have the density. The density basically normalizes the count, so no matter how small a population is, the density will always be relatively similar, so we can better compare the population of several species, because even though we have far fewer chinstrap penguins, the area under the line here is exactly the same as for the other two. And what you can see here now is that actually this chinstrap is a bit different from the Gen 2 penguin, because we have another spike here, so there are quite a few who have a longer bill, but overall the two overlap quite closely. So again, we probably see two clusters here, one for the Adderley penguin and another one for the chinstrap. So Adderley is probably rather different from the other two. Let's go on and try the box plot here. This time we choose X, the bill length, and for Y the species, and I'll show you why in a minute. So before we always had box plots that were standing up basically, and now we have them lying down because the names are still quite long, and to better display them, I put them on the y-axis so they have more room. And what you can see here is that the median, which is one measurement that you can express the variation in, is quite different from the other two. Again, to quickly explain the box plot, half of the penguins of Adderley have a larger bill length than the median, and half have a shorter bill length. And then within the box itself, there are 75% of the population of Adderley penguins, while 25% have a smaller bill length and 25% have a larger bill length. And then we don't have any outliers for Adderley here. The only species that we find outliers are Gentoo penguins, where we seem to have one that has an extremely long bill. And when we check our data set and go over to bill length and sort, we should see the exact value. We actually have two here. One is the Gentoo penguin, which is an outlier, and the other one is a chinstrap penguin, which, even though the bill is almost as long, isn't an outlier here, because 58 is just within the range of the whiskers here. And if you want to know more about box plots, you can go back to the chapter. But honestly, I would probably simply choose a different visualization if I wasn't already familiar with box plots. What I also suggested here is that you can add a geom quasi-quadrant for visualizing how many penguins are in one species, because this information is now completely omitted, and I can quickly show you what this does. And yeah, there is no namespace ggb swarm because we haven't installed the package yet. Let's quickly do this. Here we go, and now this should work. Okay, so what this tells me is that since the last time I used the package, the behavior changed, and we actually have to set one of the variables here explicitly, group on X. We want this to be false because we have the box plots lying here, so they are on the side and they don't stand upright. So let's try this, and now you can see what the function does. It basically displays a scatter plot on top of the box plot, and what you can see here is that we actually have more Gentoo and Adelie penguins, then Chinstrap. And for Chinstrap, we also don't have one solid bee swarm. So it's called a bee swarm because because it evades overplotting, and the point cloud looks a bit like a bee swarm. And we can see that here we have two distributions basically, while here we have a pretty normal distribution. We have a consistent bee swarm or cloud. To make this look a little bit better, we can also set the alpha value, because currently it hides the box plot almost completely. So here we go, or maybe even a bit lower. Let's try 0.2. And when we have this now, it's much easier to interpret the box plot, because now we can also see each individual penguin in the species here. This doesn't always work. For the diamonds dataset, for example, it looks horrible because we have far too many individual observations, and so the plot is incredibly crowded. But with the penguins dataset, I think this looks quite nice. The next alternative is the violin plot. This is an alternative to the box plot, which I quite like. It again shows a density plot, but this time instead of lines, we have the so-called violins. So they basically draw the density around the individual plots. We could put in the bee swarm here as well to visualize it, but I think it does a better job of showing that the chinstrap penguin, for example, we have two somewhat separate distributions here, while the other ones are much rounder and the distribution is more normal. But again, it doesn't show us at all how many penguins are in each species, so you could think about adding the bee swarm here as well. And then finally, we can look at the plot, which is again quite similar and has been very popular a couple of months ago, which are the density ridges. So this is actually quite similar to the violin plot, but instead of a violin, you have those ridges on each of these lines on the y-axis, and it again shows the density of the population. And here again we can see that the Adelie penguin population has a normal distribution of bill length, while chinstrap has these two distributions here, or with a little gap between the two peaks. And the Gentoo penguin population has this one peak here and then a smaller one here. Again, we have a warning here telling us that bandwidth was set to 1.08. I'm not sure what they're using to determine the bandwidth here, but I think it looks pretty good. So we can get rid of the warning by simply making this explicit. And another thing that I would probably change here is that currently you can't see the entire distribution of the chinstrap penguin because it is partly hidden by the distribution of Adelie penguin, and the same is true for the Gentoo penguin. So what we could do is we could decrease the alpha value of the ridges. Let's say we decrease it to 0.5, and now you can see the distribution in a much nicer way. So I would probably go with this plot. It's mostly due to personal taste, but I also think it is easier to communicate than the bill length here, and it just, in my opinion, looks nicer. So once I decided that one of the plots is actually pretty helpful, we can style it a bit. So I usually choose the minimal theme, which I think looks a bit nicer. And then I don't like that we have species all the way over here and bill length over here. Generally, I'm not a big fan of axis descriptions. What I like to do instead is remove them and add the information that they communicate to the title. So we want to set the label of the x, we want to remove the label of the x-axis, so we set it to null. And we'll do the same for the y-axis. And then we add a title to this plot, which I want to be distribution of bill length for different penguin species. And here we go. I think this looks pretty nice. I could imagine putting this in a journal, maybe make it a little bit wider. But besides of that, this is, I think, a pretty nice plot. If instead of a journal, I wanted to put this on my blog, for example, I think it's looking a little bit dull at the moment. So we could also add some color. Which we can do by mapping one of the variables to the fill aesthetic. And even though this doesn't make a lot of sense, I can again use the species variable. So here we go. It looks a lot more colorful. We don't need the legend. It decreases the size of the actual plot here. And since the color isn't actually adding new information, I think it's superfluous. And we can remove this by setting show legend to false. The command which actually produces the legend is the ggriches command. So we have to add the argument here. And once we remove this, now, yeah, as I said, I'm pretty happy with this plot. Now I could also do this for all of the other combinations, but as you can see, that would be quite a lot of work. We have 4 categorical variables and 4 continuous ones. So that would be 16 different combinations. And if we also take into account that we have 4 different plots, that would be 64 plots that we would have to make. So I'm leaving this up to you. You can probe the dataset a bit further and see what kind of plots you like for which sort of distribution, but I think it makes sense to move on. And I'm taking this with me and go to the categorical versus categorical variable plots. So we start with geom count, and I'm not actually sure if we looked at this before, but if we go with species and island, for example, I can show you what the plot would look like. We basically see the number of penguins that overlap in those distributions. So we see that the Gentoo penguins are only located at Biscoe. We have an empty spot here and an empty spot here. And then we see that this dot, the size of this dot, falls into the 120 range. So all of the penguins are located here. The same is true for Chinstrap, but Chinstrap are located on the Dream Island, and then only Adeline penguins can be found on Biscoe, Dream Island, and Torgenson. I'm not a huge fan of this kind of plot. I usually prefer to use the heat map, which we can find down here. So let's plug in the same data and variables here. So we have island and species, and you can run just this dplyr code here, which counts the distribution to get a table. And we can see here once again the Gentoo penguin is only located on Biscoe, and 123 penguins of the species live on this island, as you can see. Then Chinstrap, you can see it is only located on Dream, as we saw in the plot. And then Adelie penguins are spread over all of these 3 islands. So now what we want to do is to plot this table, and we can do so by mapping the island to the X aesthetic and the species to the Y aesthetic, and then we use n to determine the fill. So what you can see now is that the plot is divided into rectangles, and you can see that again, some rectangles are completely missing because there are no penguins on this island, and then the other rectangles are colored according to how many there are. Now, why is this called a heat map? This doesn't really display heat, it rather displays cold because we have a blue scale here. So what's usually done is you add a different color scheme. In ggplot, you can do this by adding scale. Then we want to change the fill aesthetic. And then since this is a gradient scale, we change the gradient. And for gradient, you have to provide two values. The color for low values in the gradient. I think we should go with yellow here, and then one value for the high values in the gradient, and here I want to go with red. And when you plot this now, you can see why it is called a heat map. This looks a bit like the picture from a heat camera now, and you can see that all the heat is on top here, and at the bottom the smaller populations, they produce a yellow color, and then in the middle we have a somewhat larger population, again according to our color scale here. Again, it would be a good idea at this point to write down our insights into the data and to write a little conclusion of the section to see what are the actual connections between two variables. But since we haven't looked at all of the different categorical variables, I think this makes not that much sense here. I'm also thinking that the connections we see here are not that interesting, so there isn't one that I want to style further, but we've also already done this, and I think we can simply move on to the last section here, which is continuous versus continuous variables. And again, let's go back to the start of this section and copy our continuous variables in here so we know that what we are dealing with, and then let's plug in our data set, the penguins data frame, and then we want to look at bill length versus body mass, because I mean this would make sense. If we have larger penguins, then their bill length is probably higher. And as you can see, we have like a slight general trend. We have an upwards connection here, but we have also some penguins which are relatively light and probably small, but have a pretty large bill length. And the idea that this gives me is that actually we are dealing with 3 different species of penguins. So what we can do is actually add another variable to this plot to see if there's a connection between not just 2 but 3 variables. And what we could do here is we could map the species to the color of the points, and when we do this, we can see that we have a nice connection between body mass and bill length for 2 of the species, for the Adelie penguins and the Gentoo penguins. And then the chinstrap penguins, they also seem to have like a general connection here. The trend is probably somewhat similar, but it is just moved to the right in this plot. So chinstrap penguins generally have a longer bill, and that explains the connection that we see here very nicely. So this is again a plot that looks pretty good, and it looks like it could be really useful for people who are colorblind, or if this is reproduced in a black and white format, we can map the species to another aesthetic. Let's take shape. Since we have just 3 species, that could make sense. Yeah, and as you see here, this looks really nice. If you imagine this in black and white, it would still work. You would still be able to differentiate between those three. And yeah, I'm pretty happy with that. So let's slap a different theme on this. Again, I'm using theme minimal, which I quite like. And I want to change the labels here. So again, I want the X and Y labels to disappear. So I assign them the value null, which simply means absolutely nothing. You could alternatively give an empty label, which is also fine, but I prefer this one. And then we can put the actual information into the title. So here I would say we have body mass versus bill length. And I highlight that this is on the x-axis. Again, you don't have to do this. It is just the way I prefer it. And then what I also don't really like is the position of the legend here. It fills up a lot of the horizontal space. So what we could do to rectify this is to further style our theme. So let's look into the theme command. Basically what theme minimal does is it sets a few defaults differently, but if you want to further stylize it, you could look in here, and when we go to legend, we see we have legend background, and here we have legend position, which is what I was looking for. And let's go ahead and copy this argument over. So we want to add a customized theme, and the values you can choose here are either the position of legends with a 2-element numeric vector. So maybe you want to put this inside of the plot here, and you decide that at 30 and 6000, this would be probably a good spot for the legend if you wanted to have it inside the plot. But we go with one of the defaults here, which is the character vector. And when I put this in now, the legend is moved to the bottom. Now, something else that you notice here is that now the long names really get in the way. We can change this using dplyr. So we move the data outside of ggplot and start a chain of dplyr commands. Especially I want to create a new column called names short. And we're creating this on the fly using case when. Case when was mentioned in the newer edition of the book. It's an alternative to if else, which was mentioned in both versions of the book that I provided. Case when, basically the way to construct a new variable based on several conditions. So if else, you can only have one test. In case when, you can have several ones. So what we are looking at here is the species. So what I could quickly do is wrap the command unique around species. I use the $sign here to indicate that the column that I want to look at is species. And when I run this now, and of course you have to. Okay, so here we have our 3 penguins. And the way you construct conditions here is by writing a test. So if the name of the species is Adeline and then in brackets Pygocelis adiliae, then we want names short to be this string. So once again, going over the first line here, we have a test, and if this test is true, then this kicks in and renames the new variable to Adelie Penguin. Or you know what? We can make it even shorter. We just call it Adelie. And then we can basically copy this line twice. And here we want to have Gentoo. And here we want to have Chinstrap. And then finally, case when expects to have a default value. So when none of these tests evaluates to true, we can simply call it other. So here this is always true, of course. And the way case when works is that it first evaluates the first test, then the second test, and then the third test. And then if it doesn't find anything, so if species is neither of those three, which we are sure it needs to be one of these three, I just evaluated the unique command down here. So we already know it's one of these three, but still I put in a default here, which is just good practice because this way it will be safer. So what's happening here is that I have the penguins data set. I make a new column called name short, which is based on the column species. And now what I can do is I can copy the name of the new column down here. So we have shape and color mapped to the new name. And when I run this now, we have nice short names here. At this point, I also wonder, do we really need the legend title here? We can remove this too by simply setting the color and shape in our labels to null as well. Here we go. The reason why I had to put in both was because the legend here actually displays the information for both the color and the shape. So a final thing that I want to do is to evade at least a bit of the overplotting here. And as we've learned last time, we do this by setting alpha to a lower value. I'm choosing 0.2 here. So it seems we don't have a ton of overplotting, so it's actually a bit hard to see. Let's try a different value. I think we can even go a further bit up. No, that was too much. So 0.6 is probably the sweet spot. So we still have a clear view of all of the points here, but we can see that up here we have a bit of overplotting. Here we have a bit of overplotting simply because the shapes are now a bit darker. And then we have two more options here to display basically the same thing. And as I explained in the slides, all of these are targeted at evading overplotting by doing something similar to what we've done above with the histogram. And when we now add the penguins dataset, or maybe let's add the whole thing here. And just use the different geom. Let's see if this works. I'm not actually sure if it can deal with color. It actually can't. Okay. So what we see here now is pretty similar to the heat map. We can go up a bit and choose the different color scheme. To make the similarity more obvious. Yeah, and now you can see that we have more penguins in this very spot on the plot and more up here. They're basically clusters which occupy this specific rectangle in the plot. But as we saw, it's not so super helpful because we don't have a ton of overplotting in the first place. And this way, we can't really have the different species in one single plot. But what we could do to include the different species is to do a facet wrap, and I want to have names new in here. No, names short. And when facet wrap is actually expecting a character value here, not just the name of the variable we want to use for faceting. So if we now put this into quotation marks, then it works, and we can see the three different distributions. I think it's actually a bit harder to see than in this plot here. This worked better, I think, so I would rather go with this one. But if we had a larger data set with, say, a couple of thousand observations instead of a couple of hundred, this would probably be the better option. And then for completeness, let's also show the geom hex plot. It tells me here that I need a different package for this, the hexband package. Okay, that's fine, let's install it. And as you can see, the geom hex is probably in the process of being incorporated in ggplot, because you don't actually have to load the package anymore, the hexbin package where this geom came from, but it's enough to have it installed on your machine so ggplot can use it. And what you can see here now is that it's very similar to geom bin 2, but instead of rectangles, you have hexagons here. And then finally, let's do another round of box plots here. So remember that box plots are made to compare continuous with categorical variables. So what we are doing here is to split up one of the continuous variables into a categorical one. So we have the cut width command in here, which is similar to the binning we saw in a histogram, for example. So let's do this. Let's add our data set. And again, we want to go with bill length and body mass. And then we want to cut up the x variable, which is bill length in this case. Okay, so the bin width that we chose is much too small. We probably want to go with, let's try 2. Yeah, now we see a nice distribution here, and we can see that bill length was split into ranges of 2. We could go a bit further. I think it's always hard to compare this many different box plots, but we can see a nice distribution here. So we have a nice upwards comparison, and then one of the bins where the median is a lot lower. When we go back to this plot, we can see that this is around here where we have a lot more chinstrap penguins, which are at the same time lighter and have a longer bill. So we already know that this is the case. I would probably increase this by a little bit so we have ranges of 5 and fewer boxes in our box plot. And then again, we can try to add the bee swarm and see how this looks like. And yeah, we have too many boxes. The distribution is basically all over the place. Also, in this case, it's not really necessary because we already have a nice distributions. We don't have a lot of overplotting. So what we could do instead here to make the box plot look a little bit better is to simply add our points. And yeah, this is fine, I think. Again, for this particular data set, the scatter plot already looks really good, and we can read from this everything that we need to know about the covariation here. So there's actually not anything else that we need. So I would probably just leave with this. Maybe we can also add the color down here just as a final reminder, so we can add color. It doesn't make a lot of sense to add it up here. I'm not even sure if it would work because, yeah, because I'm not sure if the box plot can handle this. Yeah, I mean, it works for some of them, but then here those are basically gray. What I think would be a better idea is to use the color just for the scatter plot. So we make a new aesthetic command here and then use it just down here. You can see that the legend has changed now, and that we only have color in the points. And when I look at this, actually I want to have the points behind our box plot here. And we can simply do this by changing the order of the geoms. So everything that's further up is in the background of the plot. And then for the geom box plot, what I want to do is to decrease the alpha value, so increase transparency. And let's say I want to go with 0.7 here. 0.7 here. Okay, I think this is looking pretty good. Not sure what this warning is. Yeah, if I run it again, I don't get it. So GC invocation usually has something to do with your memory. So if you have a computer with very limited amount of RAM, then you will get this repeatedly. In my case, I simply have a lot of programs open in the background, so this is probably what's going on here. Yeah, but I think this is a plot that I could live with. We could also try to implement the rich plot for this distribution here, but I think this should be enough. I realized while going through this that there are a couple of plots which we spoke about earlier that we haven't covered here, but I think you get the idea, and you can always take the slides here and add your own plots that you want to use in your project. This gets me to two last points before I close the session. The first one is that what we've done today in terms of exploratory data analysis is what I expect from you to do in the presentation. So the presentation for this course should include an exploratory data analysis of a data set of your choosing. So what I want to see is that you know how to use the different commands from the dplyr package that we learned, like rename, mutate, filter, select, and so on. I want to see that you have a basic understanding of the different data types, so you know how to spot a categorical variable, which is usually a character, or sometimes a factor variable, which we also talk about later on. Then I want you to show me that you can do the different plots and that you can gather an understanding of a data set by interpreting these plots and choosing the ones that make most sense. If you want to do a bit of further styling of the plots, that's really cool. I encourage you to do that, but if you want to stick with a default theme, that's also perfectly fine. What's really important here is that you show me in your presentation that you can basically open the toolbox, which we created in this course. You can take out the tools that are appropriate for your data, and then you can use them to understand a data set and tell a coherent story about what's going on in the data. So if you want to practice some more, I encourage you to use some of the variables that we omitted today. So we didn't look at build depth or flipper length. So go ahead and plug these in and see what you can do with the plots. And I will also leave the exercises at the bottom here that the book provided. So I will call this exercises from the book. And with that, I'm closing today's session. I hope you learned a lot and had some fun, and we'll see each other at the next face-to-face session. Bye bye.